Okay, so thanks, Chirun, for the introduction. And today I'm going to talk about our 5-year effort to push automated verification tools into the Linux kernels developer side. Okay, this is joint work with my PhD student Harishankar Vishwanathan and Matan Shaknai, who couldn't be here for various reasons, and my colleague Srinivas Narayana. So what is the context that we are looking at? Imagine you are a developer in a large streaming company. Your service is deployed on millions of machines, and they're all running on containers. And your users are complaining, man, it's buffering. Like my videos are not playing smoothly, and you want to debug it. And one way to do this is by tracking how quickly your reads are coming in. So you're an application developer, you want to extend the functionality of the Linux kernel. And you have some kernel friends, you're an application, you don't know kernel programming, you ask your kernel friends, please add me this feature to measure latency in the Linux kernel. And your kernel friends are going to say, oh, this is a kernel feature, I need to wait a long time, I need to get community input, and eventually after a year, they add a patch to your Linux, they add an extension to your Linux kernel. But this happens only in the latest version of the kernel, like 6.8 or 7.0. But you don't run. You're running a production system. You don't run the latest kernel. You are running whatever your LTS supported version of the kernel is. And you want it in my distro, right? Like your Red Hat or Fedora. And 5 years later, it becomes to your, it's backported to your distro. By this time, your company is either out of service or your requirements have changed. This is a real problem that cloud providers are facing. You want to extend the functionality of the Linux kernel. And this is where extended Berkeley packet filter system comes into the picture. What does it allow you? It allows you as a programmer, a user, to add code into the kernel, extend the functionality of the kernel. So it sits between, like, you can attach code at various points in the kernel, like you can write your code in any language of your choice, like C, Python, Rust. And then there are modern compilers allow you to generate bytecode, which would be in a restricted instruction set, and you can plug into the kernel. So you don't need to have a lot of kernel programming expertise. You can extend the kernel. And if you talk to people in industry who manage large deployments, they are just like jumping with joy. So Brendan Gregg at Netflix says, superpowers have come to Linux. eBPF provides superpowers to Linux. Microsoft is excited about BPF. And Google, similarly, any cloud provider is excited about BPF. And there is a foundation now, eBPF Foundation, which is encouraging open work to make BPF really useful and amenable. This community knows what are the ramifications of letting users write user code in the kernel, right? Okay? So BPF, the Linux kernel developers are not dumb. They're like people who really care about them. So they decided, like, we'll not let any random code get into the verifier. We are going to do static analysis within the kernel. So this is what an eBPF verifier is. Okay, so what does it do? When you have a user level program, you want to extend the kernel, you make a system call called BPF. And you give this program to the system call. So the Linux kernel checks the safety of this program that you're trying to insert. If it deems it to be terminating, if it deems its accesses are safe to kernel data structures, it allows the verification succeeds. Then it JIT compiles and generates x86 code, and that it attaches to the various hooks in the Linux kernel. Okay? So for people in this community, like, we have been doing static analysis for a long time, right? So here is the world's most widely used abstract interpreter. The Linux kernel runs on close to 6 billion devices, and it does abstract interpretation in production. Typically, like, when we do abstract interpretation, what do? We do it on the side, right? Like, our abstract interpreter runs offline, analyzes the program, proves the program safe, and then the analyzed program is run in production. Here we have an instance where the abstract interpreter itself is running in production. Okay? So we have all built abstract interpreters or static analyzers. What are the goals? We want it to be safe. We want it to be fast. We want it to be precise. Okay? So again, for this community, we know we should not accept any unsafe programs. That's a soundness. We don't, yeah, we don't want to accept, we don't want to reject any arbitrary programs. Writing static analysis in general is pretty hard. Like I've written a few, like I've had a lot of bugs, and I fixed them over a period of time. Okay, and similarly, bugs have arisen in the Linux verifier, and these are really catastrophic. If you have a bug in the verifier, you accept an unsafe program, and attackers are always, there is a huge economy out there. If you have a bug, they are willing to attack it. So they will exploit these bugs, design a malicious program, and your system is completely compromised. So what we really want, and the other thing is the analysis has to be very fast, because Linux kernel has a timer interrupt running on. Like if your verifier takes a lot of time, you would be like running out of your time slice. So this was the context when we started this project. What we really wanted to do about 5 years ago was to show the correctness of the eBPF verifier. Unlike a lot of other abstract interpreters, eBPF verifier works on a very curated instruction set. So can we formally prove the soundness of the eBPF verifier? So why was this challenging when we started out? There is no specification of what algorithms are being used. Whatever is running is actually the C code that implements the verifier. And what are the guarantees? There is a test suite that comes along with the Linux testing infrastructure. So we didn't know what algorithms like the Linux kernel developers had designed. Many of them may not have taken Kuzo's course on abstract interpretation, right? So that they may be reinventing many of the algorithms and doing it wrong. So this is where our project started about 5 years ago. And just to give you an idea of what are the static analysis in the BPF verifier, there are lots of things. One is it's a bounded program. So it wants to show termination. So it does some sort of path exploration. It has a lot of helper functions associated with it. And then Spectre and Meltdown are huge attacks. So it does not want any side channel leakage of information. So there are side channel mitigations. So this entire web eBPF verifier is about 20 to 25,000 lines of C code. Okay? And the specifically what we focused on is the value tracking aspect of it, where it tracks the values of variables. And it uses 5 abstract domains to do this. A bitwise domain by Anton Moyne, so where each bit is a known 0, known 1, or unknown. So the kernel calls it tnums, tri-state numbers. So, and then 4 kinds of interval domains, signed and unsigned domains with 32 and 64. So the value tracking component was about 6,000 lines of code, C code. So when we started this project, we first, let's look at the bitwise domain, because Anton Moyne had like classical papers on it. And Linux kernel reinvented it, even named it, and gave it a new name called tnums. And we couldn't prove the correctness of it. So we manually encoded the kernel's implementation into SMT formula, tried to check the correctness. In some cases, for multiplication and division, the SMT solver would time out. So we wrote paper and pencil proofs to show the correctness. And in some cases, we couldn't even write the paper and pencil proof. So we designed new algorithms for which we could write paper and pencil proofs. And the kernel developers were very receptive. Oh, like you have a paper and pencil of proof of this correctness? They upstreamed our algorithm into the Linux kernel. But one thing what we realized in this exercise is this business of manually translating their logic into your SMT conditions or your proof assistant theorems is very challenging. So it's not feasible. Like if you want our tools to be used by kernel developers, this is not going to make any headway. So we wanted some automation. Subsequently, in our CAV 2023 paper, we automated this entire system. So what do? We take the implementation of the abstract operator in the Linux kernel source code. We automatically generate SMT conditions encoding it. And then we have a soundness specification, and we check is the implementation sound. So here, we got traction from the developers. We showed about 26 kernel versions. We studied 26 kernel versions, found bugs in many of the kernel versions, and showed some of the other kernel versions, the verifier versions, to be correct. And we got traction. Kernel developers got excited. And then about a year ago, there was a new patch to the eBPF verifier, which significantly enlarged it. And our verification started to time out. Okay, and then what do we do when something times out with the automated verification? You divide and conquer, right? We split it into small parts, and we wanted to verify the individual parts. To do that, we wanted each individual part to be correct, sound, and then we can write a compositional proof. And it turned out that the Linux kernel's abstract operators individually, the individual parts were unsound, and we couldn't compose the individual parts. So then what we did was we fixed this unsound parts so that we designed a sound algorithms for this abstract operators and upstreamed it. So what I'm going to tell you in the next talk is like this entire process of how we automated it, why was it unsound, and how we fixed it. Okay, so if there's one thing I want you to take away from this talk, so many of the design decisions that we had in this project is dictated by our need to automate, to push automated verification. So we wanted kernel developers to use it as part of their continuous testing infrastructure. Like people are pushing patches almost like every month to the eBPF verifier. And I or my students cannot be sitting there and verifying it. We want the developers to use these tools and verify it. And to do that, they should have a seamless path of integration. So many of the design decisions are primarily motivated by this use case. Okay, so let me give you an overview of AGNI. Okay, this is our tool where we automatically encode the working of the abstract interpreter. So here is your Linux kernel C verifier source code. And this encodes your abstract operators. For every concrete, like if you have an addition, you have a corresponding abstract addition, done with intervals or done with tri-state numbers or bitwise units. Roughly, this is 6,000 lines of code. So what is, like now we want to encode them into a mathematical formula. What is the challenge in doing it? So the challenges are, like it uses kernel data structures. It uses kernel header files. It uses kernel data structures. If you look at it in isolation, it's going to be very challenging to deal with. So to translate it into SMT, or a first order logic formula, we build an infrastructure using the LLVM compiler. So why the LLVM compiler? Because now we don't have to worry about like all preprocessor headers and other things. When we compile it, if we generate the intermediate representation, everything is included. And then we don't want to look everything all at once. So if we are looking at an add operator, we don't want to be looking at and combining everything. So we use dead code elimination, which is already built in the compiler, to slice out only the operators of interest. Okay? So the other thing that we need to do now is when we generate SMT formula, we want to use bit vector theories because they are reasonably fast and you can complete verification quickly. We don't want to use theory of arrays. But if you look at the kernel code, like the abstract interpreter state is encoded as a structure stored in memory. So we need to create a view of memory and update it as these memory locations are updated. So without using theory of arrays or any heavyweight reasoning methodology. So again, our primary goal is verification. So we use memory SSA to make this view of memories feasible. And we encode the memory using an array of bit vectors to accomplish. So the end result is we end up with a collection of mathematical conditions, a mathematical formula that encodes the operation of the abstract operator. Okay, so then we couple it with our soundness specification, which I'm going to describe in a few slides. So if our automated tool says it's unsound, just saying it's unsound to a verifier, to the Linux kernel developer is not going to help them. So we are going to synthesize a concrete BPF program. You're going to take this program and run it in the Linux kernel. It will show the difference between the abstract semantics and the concrete program semantics. So we use a technique called differential program synthesis because we're synthesizing a program which shows the difference between the two semantics. You can run this program in an emulation environment that we built for Linux using QEMU. So now you can show the difference. This entire infrastructure was essential for kernel developers to accept our patches, acknowledge our bugs, and even like get the communication going along. Okay? So now what do I mean by an abstract operator to be sound? So you have an addition. You encoded addition with using abstract values, right? Like now, let's say you have an abstract operator. This is an abstract operator for addition. So it has two operands, two input operands, which is your two abstract states. It produces a resultant abstract state. Okay? And then you have a concrete function, which is your concrete addition. It takes two inputs and produces a concrete output. So what do I mean by soundness condition? Provided if the input concrete values are members of this input abstract states. So how do I represent this as a predicate? Like for example, if I have an interval is represented by a lower bound and upper bound. Let's call it like say 64-bit integers. That's what it happens in the kernel. The predicate would be like if the concrete value is greater than or equal to your lower bound and concrete value is lesser than or equal to your upper bound, that is your predicate that you define for membership. And what you really want is the resultant value to be a member of your resultant abstract state. And you want this to be true for all input abstract states for this abstract operator. So now to present it as a complete mathematical formula, P and Q belong to your abstract state, X and Y are concrete values, X is a member of P, and Y is a member of Q, and Z is the concrete value produced from a concrete operation, and R is a abstract value produced from your abstract operator. It better be the case that Z is a member of R. This is a soundness condition. So again, we have abstracted the concretization and the abstraction functions. We're using these predicates. Okay, so the Linux kernel uses 5 abstract domains. The tri-state numbers is the bitwise domain. And then there are signed 64-bit domain, unsigned 64-bit domain, unsigned 32-bit domain, and signed 32-bit domain. So when you have 5 domains, what is your abstract domain? It's a Cartesian product of all these domains. And how does the soundness formula change? Your resultant value has to be a member of each of the subcomponents of this product domain. Okay, so this is again, the details are there in our CGO and CAV papers. So this is an experience report as well. So like, what did we experience? So we built this tool. We were excited. We have the soundness conditions. We tested out with 26 versions of the Linux kernel, starting from 4.14. And our verifier said all the kernel versions are unsound. And for many of the initial versions, 4.14, 5.1, we could actually generate concrete programs where they were unsound. But like, for all the versions, for some of the later versions, 5.15, we couldn't generate a concrete program where the abstract and the concrete semantics mismatch. So maybe we had a bug in our encoding. We invested a lot of time. So to talk to the developers, we wanted to like give them concrete programs. So this is like a false positive in static analysis, right? But we are not producing a concrete observable program that can demonstrate it. So we spent about 6 months trying to identify why is our verification tool saying these programs are, the eBPF verifier is unsound, at least for the later versions. And then my student was eyeballing the code. This is what the abstract operator, the high-level abstract operator, looks in the kernel. It takes some concrete ops and other things. There's a big switch statement. If this is an add operation, do the abstract add. If it's a sub operator, do the abstract sub. And mul, do the mul. And at the end, there is this function called sync. And we were curious, what is the sync? And it turned out the kernel is building a refinement operator at the end of it. So this is a shared refinement operator in the abstract interpretation. It has multiple domains. It wants to learn something from each of these domains. It has a refinement operator at the end of it. So now, let's go back to the concrete picture that we had. When we try to synthesize a program that demonstrates the difference between the two programs, so what's happening? The first instruction, you get the initial abstract states. For the subsequent operations, for the subsequent instructions, the input abstract states are outputs of a shared refinement operator. So in our soundness condition, we wanted it to be true for all inputs, for all input abstract states. But for any subsequent instruction, your input states are all preconditioned by the shared refinement operator. And when we did this, so effectively what we said is like your input states to this operator is preconditioned by the shade reduction operator, and then we verified it. Now we could prove the correctness of some of the later versions of the Linux kernel. And for whenever we couldn't prove soundness, it turned out that we could generate a concrete program that shows the difference. Okay, so everything was great till now. So after this, like kernel developers started using our tool, and they were using it in production. And around a year ago, Andrew Narco submitted a patch to the shared refinement operator, and our verification started timing out. Okay, this is the trouble of success, right? Like they start using our tools, and now you time out. And now what can we do? So we started analyzing it, and then this entire abstract operator was about 5,000 lines of SMT formula. And internally, there is the abstract operator and the shared refinement operator. The abstract operator was 700 lines. The shared refinement operator was 3,000 lines. We wanted to individually verify their soundness. So how do we check the soundness for the abstract operator? We do it as before. We take the concrete function, and the resultant state is a member of it. And what do we do for the shared refinement operator? The shared refinement operator takes only one input, which is the abstract state, and for every concrete input that is a member of the input abstract state, it better be the member of the output abstract state. And also, this output abstract state is a refinement of the input abstract state. That's the definition of refinement. And when we try to validate the soundness, the abstract operators were unsound. Okay, and the shared refinement operator was sound. We could compose the proof. Now, to make the verification succeed, we had to fix the error, this latent unsoundness in the operator. So just to give you a structure of how the abstract operator is written, there is tnums, the tri-state values, then the interval domains, they are all used. And when we looked at the code for the interval 64-bit domains, what was it doing? If the values are negative, either one of the operands are negative, it's just unbounding the sign domain. Otherwise, it was using the 64-bit domain values to update the signed 64-bit, unsigned 64-bit abstract values to update the signed 64-bit values. You cannot cast unsigned 64-bit values to signed 64 values always. And this was the source of the bug. So our idea is, when can you safely assign a 64-bit unsigned 64-bit value to a 64-bit value? So if you have a 64-bit value, 2 power 64 to the power of 63 minus 1 is the boundary. If the value, if both, if the minimum value and the max value in unsigned domain is less than 2 to the power of 63 minus 1, you can safely assign it. If it is both greater than 2 to the power of 63 minus 1, even then you can assign it. If the min and the max straddle the this 2 to the power of 63 minus 1 boundary, then you cannot safely assign it. Okay, so our patch that we had to the kernel was to assign it only when it's safe to do so, and it does not straddle the boundary. Okay, we proved it with our automated checker. This is actually a sound. And with this fix and the divide and conquer strategy that we had, we could prove the correctness of all the kernels, and each individual operator is also sound. And now there was a talk at Linux Plumbers given by a kernel developer relating his experience using Agni, which is our tool, to validate various versions of the kernel. So the patches and the new algorithms that we have designed for various abstract operators have been upstream. They're all part of the Linux kernel, some of them since 4.14. And the integration of our tool into the Linux CI is happening now. To summarize our experience in a nutshell is Linux kernel developers deeply care about formal methods. So this is an opportunity for this community to engage with them. Okay, so you have to speak their language as well. If you have a collaborative approach where you engage with them, so it's feasible to push formal methods into the Linux kernel's toolchain. So all our code is available on the website, and I will be happy to take questions now.
So you showed us that you had a version that was not verifiable, and then you showed us a change that you made, and then you showed us a version that was verifiable. But is there any kind of deterministic pathway that got you from the non-verifiable one to the verifiable one? Is there something that you could see that guided you towards the correct change, or?
That's a great question. So this is where, like, with our tooling, we generate counterexamples at every step. So when we did not verify, we had a counterexample, and we used this counterexample, and we built this schema engine, right, where we could run the verifier and print out the actual abstract state and look at the concrete state. So we looked at this, and why is this happening? And then we saw, oh, like, we observed that sign bound, the min bound is positive and the max bound is negative. And that's when, like, it stuck to us, oh, there is unsafe casting going on. And that's the part.
Okay, thank you.
I was just curious whether you're exploring other parts of the verifier. You mentioned you're right now focusing on the value analysis.
So I think we are, like, for example, Hari is working on how do, there is a straight pruning logic, like it's a bounded program. It enumerates every possible path, and blindly enumerating every possible path takes a lot of time, so it has a pruning strategy. So, and it uses like some really complicated esoteric logic that even kernel developers don't know, so we are exploring those. There are Spectre and Meltdown, like basically side channel mitigations, which are like a hodgepodge of hacks that have been added, but no one has a structured idea about how to verify those. So we are exploring those, but we don't have any concrete results that we can provide to the community yet.
Thank you for the nice talk. So it seems that this reduced product operator was somehow fixing the unsoundness. Did you investigate what was going on inside this reduced product, that it fixes it, and does it actually fix it, or were you just unable to get the counterexample?
So the way, so people, the developers build these abstract operators. They wanted to do away with as little work as possible in this abstract operator. And then they had a heavyweight hammer that would somehow nail down all this. The share reduction operator, the same, was this heavyweight hammer that would flatten out all the sloppiness that other operators have induced. That's a very bad way of designing. Like generally, like if you read like traditional abstract interpretation literature, modular sound composition of sound operators, right? That would be the idea that anyone would design. But these are practitioners designing abstract operators. They've got their code to work, and they had like many of them are doing it not as a full-time job, right? Like they're like freelancers doing it as part of some other task. So I'm a bit more sympathetic to that, but I think you're dead right. Like, if you're designing abstract operators from scratch, this is not what we would do.
All right, I think we should get to the next speaker.
As far as I've understood, in certain cases, they rely on the tri-state domain to be better, and they just forget about what they do with the intervals. And